So we've been working with antiderivatives. We defined what an antiderivative was yesterday. We gave new notation, which is this integral notation to represent that we're taking the antiderivative of a function. So the notation, this is the integral of f of x dx, which means I'm taking the integral of the function f of x with respect to x. This is equal to capital F of x plus c. So we talked about the capital letter of our function that represented the antiderivative for this class. And c is just some arbitrary constant, means that f is the antiderivative of little f. And if we take the derivative of our antiderivative, we should get back our original function f of x for all x in the domain of f. Okay, so we're working backwards, and we saw these important rules, basic integration rules that are in front of us. If we took the antiderivative of a constant, that was just the constant times x plus c. That was our constant rule. If we had a constant times some f of x dx, and we were taking the integral of that, we could pull that constant out, take the antiderivative of f of x dx, and then multiply that by the constant. If we had more than one term in there, when we were taking the antiderivative, we can break it down as the integral of each term, and with a plus or minus in between, and that's our sum rule or difference rule. And then we have that general power rule. As long as our exponent was not -1, if we were taking the antiderivative of x to the n dx, then we're going to add 1 to our exponent, divide by our new exponent, and add that c. So we were going through those values yesterday, and we started to look at the antiderivative of our trigonometric functions. So let me just give you the general rules, and we've covered some of those already. So again, if our function was x to the n, we're going to add 1 to our exponent, divide by that new exponent, plus c, as long as n is not -1. If n is -1, that's our function 1 over x. And recall, what we took the derivative of and got 1 over x was the natural log of x plus c, where x can't be 0. So we talked about sine of x. We didn't say sine of kx. If we had some coefficient in there, sine of some constant times x. So let's just let's look at it if we weren't. Let's look at like y equals sine of k times x. And let's say we wanted to take the derivative of this. Remember, we were looking at the chain rule where we had to take the derivative of the outer. And so the outer was this sine. The derivative of sine was cosine, right? Of the inner, kx. But then we had to multiply by the derivative of the inner. And if we multiply by the derivative of the inner function, derivative of kx is just k. So we have to keep that in mind when we're going backwards, because we want the original. We don't want this k in here, right here. And so we need to think about it that we have to divide by what we would take the derivative of in the inside. So if I was looking at the antiderivative of sine k of x, I think about what do I take the derivative of to get sine? Well, negative cosine would give me positive sine of the original kx, but we would have to divide by that k. So that would cancel out, plus c. So for those trig functions, basically, if you have some coefficient, sine or cosine of some coefficient x, then we have to divide by that coefficient of whatever, taking that trigonometric function of. Okay, so cosine of kx, that would be 1 over k sine kx plus c. Secant squared of kx, derivative of secant squared, or derivative of tangent x is secant squared. So it would be 1 over k tangent kx plus c. The derivative a cotangent, negative cotangent, gives us cosecant squared, but we have to divide by that k because of the k out front here. And so I can continue on. It's basically all these trig functions we looked at yesterday. We just have to, if there's a coefficient in front of that x, we have to divide by that new coefficient. E to the x, that's one of the easiest ones to take the derivative of, because the derivative of the e to the x is e to the x. So what can we take the derivative of to get e to the x? Well, that's also e to the x. The problem is if we have that coefficient of k in our exponent. And so we have to, again, take care of that. And that's why we're going to divide by this k in here, if this was e to the kx. So if we were to take the integral of e to the kx, the integral of e to the kx divided by k plus c. And we could check that, right? This was our antiderivative. We can check it by taking the derivative of this. We better get back what we were taking the integral of, which is called our integrand. And so if we did that, taking the derivative of e is itself e times, this is a chain rule, the derivative of our exponent, which is k, all over, we have this k here, and derivative of a constant is 0. And so now our k's cancel, and we're just left with a ek to the x. Which was our integrand. So some of your homework might just say, here's your integral. This is what it's equal to. I want you now to check it. Show me that this is really the integral of this function. And you would do that by taking the derivative of the integrand, or the whatever you found the integral to be. You kind of have to remember backwards of what the inverse trigonometric functions were. So if we took the derivative of sine inverse of kx, that was that 1 over the square root of 1 minus k squared x squared. So if you see that, and we're taking the integral of this, and this is what we're going to get back. So recognizing what you would get if you took the derivative of your inverse functions, you have to recognize if we take the integral of that, we're going to get back the inverse trigonometric function. Okay, so let's grab some examples and look at those. Okay, so our example that we pulled is the integral of 1 over x minus 5 all over x squared plus 1 dx. So we can rewrite this using our rules of derivatives. And let's just do that for now, but normally I don't write this out. But we have the integral of 1 over x dx minus, let's pull that coefficient. This is like 5 times that fraction 1 over x squared. So let's pull the 5 outside of our integral of 1 over x squared plus 1 dx. So looking at what we take the derivative of to get back 1 over x, that's the natural log, absolute value of x, minus this 5. And so this 1 over x squared plus 1, that looks like the derivative of tangent inverse of x. So this would be tangent inverse of x plus some constant c. So what about I don't know, let's say 1 plus cosine 4 of t. And this is all over 2. And this is dt. So looking at this, I don't know how to integrate this yet, but I notice I can rewrite this and we can break this down into a sum of 2 fractions. And so let's rewrite it first. And so that would give us the integral of 1/2 plus cosine of 4t all over 2 dt. So we're looking at the integral of 1/2 dt plus, if we want to, we can bring that 1/2 out of the integral, 1/2 cosine of 4t dt. So the integral or antiderivative of a constant is that, and we're variables in terms of t, not x. So this would be 1/2 t plus 1/2. So we're thinking to ourselves, what do we take the derivative of to get cosine? Well, the derivative of sine is cosine. So sine of the inside 4t. But because that has a coefficient of 4 in front of that t, we have to divide by that coefficient of 4. And then we have some constant c that we're adding. So we have 1/2 t plus sine of 4t, 2 times 4 in our denominator, so 8 plus c. So finding the antiderivative can help us with some applications. So remember, we're adding c all the time here. And so maybe there's times where we have information where we can find what that constant is. For example, and these are called initial value problems. So let's say you were given that dy dx. So we are given what the derivative is. We're given that the derivative is 2x minus 7. We're also given that y sub 2. So when x is 2, our y value we get back is 0. And we want to solve the initial value problem. That's all it just tells me in the directions. So we want to figure out what y sub x is. So we know that if we take the derivative, the antiderivative of both sides. So I'm basically taking the integral of both sides of my equation. So let's multiply both sides by dx. So this would be the integral of dy is equal to the integral of 2x minus 7 dx. So the antiderivative of 1 dy is just y plus some constant c. I just have to write that constant once though, so I'm not going to put it in there. Is equal to, okay, so now let's take the antiderivative of 2x. So that told me I had to add 1 to my exponent. So I have 1 plus 1, which is 2, divide by my new exponent, which is 2, minus 7. Well, the antiderivative of 7 is 7x, plus some constant c. Let me just clean it up a little bit. So this is the same thing as y equals x squared minus 7x plus c. But we're given an initial value. So when x equals 2, y is 0. And so we can figure out then what c is. So y is 0. This is equal to when x is 2. So 2 squared minus 7 times 2 plus c. So we get 0 is equal to 4 minus 14 plus c. 0 is equal to negative 10 plus c. So our constant has to be 10 in this case. So knowing that, our function y, or y sub x, is equal to x squared minus 7x plus c, but c is 10. So we were able to find the initial equation given the rate of change or the derivative of a function and the initial value. Okay, so let's look at another one. So in this case, we have, how about ds dt? Actually, let me change them in terms of x and y's. How about dy dx? This is equal to cosine x plus sine x. And we're given that y sub pi equals 1. And we want to find our original function y. So again, we can think of this as the same thing as dy equals the cosine x plus sine x dx. And you can integrate both sides. So the antiderivative of 1 dy is just y equals the antiderivative of cosine of x. So that's sine of x. The derivative of negative cosine of x gives me positive sine of x. So antiderivative of sine of x is negative cosine of x plus some constant c. So now let's go in and plug in our values. So when x is pi, we get that y is 1. So we have 1 is equal to sine of pi minus cosine of pi plus c. So 1 is equal to sine of pi. So if you have to look at the unit circle, pi is here. Sine is your y value or your point on your unit circle, so that's 0, minus cosine of pi over here, that's negative 1. So minus negative 1 plus c. So 1 equals 1 plus c. So our constant in this case is actually 0. So our y function, our original function is y equals sine x minus cosine of x. So maybe instead of given the first derivative, maybe you were given the second derivative of a function. And you are asked to find the original function. So let's say in this case, you're given that d So let's say d squared r all over dt squared. This is equal to, where did it go? 2 over t cubed. And they tell us that dr dt, so the derivative of r with respect to t, when t equals 1 is 1. And it also tells us that r of 1 is 1. Okay, so we're given the double derivative. So we can figure out what dr dt is. The first derivative, if we take the integral of the second derivative. So 2 over t cubed. So dr dt, this is equal to, well, let's rewrite it again. So this is the same thing as 2t to the negative third power dt. Okay, so let's take the antiderivative of 2t to the negative third power. So we're adding 1 to our exponent. So negative 3 plus 1 is negative 2. We're dividing by our new exponent of negative 2, and then we're adding some constant c. So we have the derivative dr dt is equal to negative t to the negative 2 power plus c. But we're given, if t is 1, then dr dt is also 1. So we have 1 is equal to negative 1 raised to the negative 2 power plus c. Well, 1 to the negative 2 power, we can bring that down to the denominator and make that a positive exponent, which is still 1. And so we have 1 equals negative 1 plus c. So if we add 1 to both sides, we get, in this case, c is 2. So far we have what the first derivative is. So our first derivative, dr dt, is equal to, I'm going to leave it in negative exponent form, negative t to the negative 2 power plus c, so plus 2. So if we take the integral of both sides, we could get what r is. So r is equal to the integral of negative t to the negative 2 power plus 2 dt. So add 1 to our exponent, adding 1 to negative 2 gives us negative 1. Divide by our new exponent of negative 1. Plus the antiderivative of 2 is 2t. And then we have to add our c. So we're given r is negative over negative, so that's t to the negative 1 plus 2t plus c. So now let's use the fact that r sub 1 is 1. So when t is 1, r is 1. So you have 1 equals 1 to the negative 1 plus 2 times 1 plus c. 1 to the negative 1 power is 1. 1 plus 2, so we have 1 is equal to 1 plus 2 is 3 plus c. So in this case, c is -2. So now we know what our original function is. Our r value, or you can write it as r sub t if you want, is equal to, let's rewrite this, t to the -1 power is 1 over t plus 2t plus c, but c is -2, so -2.